Welcome to Daikin web-based training. In this course, we will be learning about simple heat load calculation. In the summer, heat enters the indoors from the outdoors. In order to maintain the comfort level of the indoor areas, the heat that has entered must be removed. The amount of heat that must be removed is referred to as the cooling load. In the winter, heat escapes from the indoors to the outdoors. In order to maintain the comfort level of the indoor areas, the room must be heated. The amount of heat that must be provided is referred to as the heating load. The cooling and heating loads together are referred to as the heat load. Heat load calculation refers to the calculation of the cooling and heating loads. Usually, software is used to calculate them. The results of the calculation are used to determine the cooling and heating capacities of air conditioners. The purpose of this course is to understand the basic idea of heat load calculation. We will first go into an explanation of how to obtain the cooling load. It will be followed by a simple look at how to obtain the heating load. The more accurately one wishes to calculate the heat load, the larger the required number of formulas and data. However, we will try to simplify it as much as possible, so you can learn how to obtain the heat load in an easy-to-understand manner. Now, let's learn about how to obtain the cooling load. There are 4 types of cooling loads. The first type is the heat load caused by the sun's rays. The roof and exterior walls of a building heat up when they receive direct sunlight. This heat then enters the inside of the building. Sunlight can also enter a building through the windows on the exterior walls. The second type is the heat load caused by the difference in temperature between inside and outside the room. When there is such a difference, heat enters the room through the building's roof, exterior walls and windows on the exterior walls. Heat can also come in through the interior walls, ceiling and floor. The third type is the heat load due to internally generated heat. Humans have a high body temperature and generate heat. Lighting and other electric appliances also generate heat. The fourth type is the heat load due to outdoor air. Hot, humid outdoor air can find its way indoors through gaps around window sashes and doors. It can also enter through vents. These heat loads are used in order to calculate the cooling load. The cooling load is calculated using 8 items. The first is the heat load from windows on the exterior wall. This is calculated using the heat load from the sun's rays and the heat load from the difference between the outdoor and room temperatures. The second is the heat load from the roof and exterior wall. As is the case with the windows on the exterior wall, this is calculated using the heat load from the sun's rays and the heat load from the difference between the outdoor and room temperatures. The third is the heat load from the ceiling, floor and interior walls. It is the heat load due to the difference in temperature between inside and outside the room. The fourth is the heat load due to drafts. The fifth is the heat load due to heat generated by lighting. The sixth is the heat load due to heat generated by electric appliances. The seventh is the heat load due to heat generated by human bodies. And the eighth is the heat load due to outdoor air intake for ventilation. Let's take an example in order to calculate the cooling load for a room. Let's define the conditions for this example. The building is located in Tokyo. The room is in the southwest corner on the middle floor of a 5-story reinforced concrete building. It is being used as an office. The adjacent hallways and rooms, as well as the rooms on the floors above and below, are not air-conditioned. The room temperature and relative humidity have been assumed as 78.8 degrees Fahrenheit and 50%, respectively. The outdoor temperature and relative humidity have been assumed as shown in the table according to the climatic conditions of Tokyo. These levels change with the time. The floor area of the room is 1,500 square feet, and the height is 10 feet. The north face of the room is adjacent to a hallway and has 2 50 square foot windows. The east face is adjacent to another room. The south face is 60 feet in length, with 4 40-square-foot windows and no blinds. The west face is 25 feet in length, with 2 40-square-foot windows. The materials used around the room are as shown in this slide. The exterior walls, interior walls, ceiling, floor, and windows are constructed in this manner. The particular structure of these items has an effect on the heat load that enters from the outside. Let's now calculate the cooling load using the above-mentioned conditions. Let's determine the heat load from the windows on the exterior walls. This table shows the heat load per square foot of window on the exterior wall. The figure you see is the total of the heat load from the sun's rays and that from the temperature difference between inside and outside the room. This table was created based on the calculation results referring to various types of data. Similar tables can be created using computer software for the calculations. As the outdoor temperature changes with time, so too does the heat load. The heat load from the sun's rays not only changes with time, but also with direction. This table tells us the following. In Tokyo, the maximum heat load on the north face is at 1800 hours. On the east face, it is at 900 hours. On the south face, it is at 1200 hours, and the west face, 1600 hours. The highest heat load among all of these is on the west face, followed by the east face. Now, let's calculate the heat load for this office. The total window area on the south face is 160 square feet. The heat load at 900 hours is 32.8 BTU per hour square foot. Therefore, the heat load from the south-facing windows is calculated as 5,248 BTU per hour. We can calculate the heat load for the time period between 1000 hours and 1800 hours in the same manner. The west face also has a window area of 80 square feet, so the heat load can be calculated in the same way. When the heat loads from south and west-facing windows are combined, the result shows that the maximum heat load occurs at 1600 hours, with the figure coming to 19,848 BTU per hour. Let's calculate the heat load from the exterior walls. This table shows the heat load per square foot of exterior wall in Tokyo. The figure you see is the total of the heat load from the sun's rays and that from the temperature difference between inside and outside the room. The table has been prepared in the same manner as the one for the windows. The heat load from the exterior walls is smaller than that calculated for the windows. It too changes with time and direction. The maximum heat load on the north face is at 1800 hours. On the east face, it is between 1100 and 1400 hours. On the south face, it is between 1500 and 1800 hours. And on the west face, it is at 1700 hours. The west face has the greatest heat load, followed by the east face. Now, let's calculate the heat load for this office. The area of the exterior wall on the south face is 440 square feet. At 900 hours, the heat load is 3.1 BTU per hour square foot. So, the heat load is calculated as 1,364 BTU per hour. We can calculate the heat load for the time period between 1000 hours and 1800 hours in the same manner. The west face also has an exterior wall area of 170 square feet, and the heat load can be calculated in the same way. When the heat loads from the south and west-facing exterior walls are combined, the maximum heat load occurs at 1800 hours, with the figure coming to 7,754 BTU per hour. Let's total the heat loads from the windows and exterior walls that we have calculated to this point. The maximum heat load occurs at 1600 hours, with the figure coming to 26,854 BTU per hour. The windows on the west face have greatly contributed to this figure. Let's calculate the heat load from the ceiling, floor, and interior walls. When the adjacent areas, such as the hallways, next rooms, and rooms on the floors above and below, are not air-conditioned, the temperature difference causes heat to enter the room. This table shows the heat load per square foot of ceiling, floor, and interior walls. The heat load changes with time. For our calculations here, we will use the value at 1400 hours that reaches the maximum. The floor area is 1,500 square feet. The heat load per square foot is 2.0 BTU per hour, resulting in a heat load of 3,000 BTU per hour for 1,500 square feet. We can calculate the heat load from the ceiling, interior walls and windows on the interior wall in the same manner. The total comes to 8,875 BTU per hour. Let's now calculate the heat load from drafts. Hot, humid outdoor air enters through gaps around window sashes and doors. This table shows the heat load from drafts per cubic foot of room volume. For the calculation here, we will use the maximum heat load of 0.085 BTU per hour cubic foot. The floor area is 1,500 square feet, and ceiling height is 10 feet. Therefore, the room volume is 15,000 cubic feet. The heat load per cubic foot is 0.085 BTU per hour. So, the total heat load for the room comes to 1,275 BTU per hour. Now, take a look at the heat load from lighting. The heat load from incandescent light equals its wattage. For example, 5 100-watt light bulbs would indicate a heat load of 500 watts. Because fluorescent lights use a stabilizer, the heat load is calculated by multiplying the light bulb wattage by 1.16. For example, 5 20-watt light bulbs would indicate a heat load of 116 watts. Now, take a look at the heat load from electric appliances. The office has electric appliances such as PCs, printers, and hot water pots. These create a heat load because they generate heat. In the case of an office like this, the total heat load from lighting and electric appliances can be estimated as 3 watts per square foot, or in other words, 10.2 BTU per hour square foot. The office's floor area is 1,500 square feet, so the heat load would be 4,500 watts, or 15,300 BTU per hour. Let's now look at the heat load from human bodies. If people are working in the office with a room temperature of 78.8 degrees Fahrenheit, the heat load per person would be somewhere around 427 BTU per hour. The floor area commonly used per person is estimated at 55 square feet. Therefore, the heat load per square foot of floor area is 7.8 BTU per hour. The office's floor area is 1,500 square feet. The heat load per square foot of floor area is 7.8 BTU per hour. So, the total heat load would be 11,700 BTU per hour. Lastly, we will look into the heat load from outdoor air intake. The outdoor air has the same temperature and humidity as drafts. The table shows the heat load per cubic foot of outdoor air intake. Here, we will use the value of 900 hours, when the heat load reaches the maximum. Outdoor air is taken in to supply oxygen to those in the room. It can also thin out irritating odors, or cigarette smoke generated indoors. The more outdoor air is taken in, the better. However, the problem is that this proportionately brings hot and humid air indoors and increases the cooling load. This is one reason why we use the minimum required volume of outdoor air in the calculation, obtained from the related regulations and data. According to Japanese law, approximately 700 cubic feet per hour of air must be ventilated per person in an office. For the calculation here, we use 880 cubic feet per hour. When discussing body heat, the floor area per person in the office was assumed as 55 square feet, so the required volume of ventilation per square foot would be 16 cubic feet per hour. In this case, the floor area is 1,500 square feet. The required ventilation per square foot is 16 cubic feet per hour, and the heat load per cubic foot of outdoor air intake is 0.85 BTU per hour. Therefore, the total heat load for the office would be 20,400 BTU per hour. We have now calculated the cooling loads for 8 different items. The results from our calculations show a grand total of 84,404 BTU per hour. This works out to 56.3 BTU per hour per square foot. Let's now learn about how to obtain the heating load. In the same way as the cooling load, there are 4 types of heating loads. Heat enters the indoors through windows on the exterior walls, exterior walls, and the roof. Due to the difference in temperature between inside and outside the room, heat escapes through the windows, ceiling, floor, exterior walls, and interior walls. There is also heat internally generated from human bodies, lighting, and electric appliances. There are also drafts that enter, as well as air intentionally taken in from the outside for ventilation. The heating load is calculated in the same manner as the cooling load. However, the heat loads from the sun's rays and internally generated heat are not usually considered when calculating the heating load, because they provide heat indoors. These are the conditions for the heating load calculation. In this case, the room temperature has been assumed as 71.6 degrees Fahrenheit, and the relative humidity as 40%. The outdoor temperature and relative humidity have been assumed as shown in the table according to the climatic conditions of Tokyo. These levels change with the time. The other conditions are assumed as the same as those used in the cooling load calculation. The heating load has been calculated using the above conditions. The calculation results in a grand total of 76,742 BTU per hour. This works out to 51.2 BTU per hour per square foot. Here is a summary of heat load calculation. There are 4 types of heat loads. These 4 types are calculated in heat load calculation. Heat load changes according to the region, direction, and time. It also differs with respect to the use and structure of the building in question. These factors must be considered when calculating heat load.